you very much, complimentary. I'll get you back there. I find myself in something of a pickle. I unintentionally, unknowingly, have written a talk that is something of a said contra to my good friend and mentor, Steve Barr, who has been a great supporter and friend for many years. I seriously considered running out at lunch and just rewriting something else in the hour and a half I had. But I decided that I will just leave this to God's providence and trusting in Dominican formation. At significant moments when we are making the bishop, we are making vows, there's a line that is asked all the brothers there, what do you seek? And the response is always, God's mercy and yours. So, Steve, God's mercy and yours. So, I want to begin with something of a personal anecdote. I'm here speaking as a physicist, but also something of a philosopher, perhaps a slightly amateurish one. But although I'm here to give this talk on physics and philosophy, my first foray into philosophy didn't really go so well. It was freshman year, this freshman humanities class at Caltech, and it was bad. It was just bad. It was a historical survey class. It started with Descartes. Now, don't get me wrong, I love Descartes. I love reading Descartes, but at the time, it just seemed odd. Without any context, Descartes sounds kind of pretentious and whiny. Let's just throw out everything that came before, just start over. Trust me, it's all crap. We'll figure this out. I mean, there's 2 millennia of philosophy before Descartes, and in fact, there's methodology behind what he's doing and he's arguing. But in the context of, that was me. In the context of that, in the context of that class, it just sort of hits you as, yeah, let's just doubt everything and start over. And my strongest memory from that class is this philosophy professor trying to get the class to take seriously the question of, what if we're all just brains in boxes? Dating myself, what if we're all living in the Matrix? This is Caltech, right? So physicists, biologists, engineers, I mean, there's some math majors that are weird, but most of us were there to study the real world, to study physical things, and we were fascinated by it. And we saw the power and the possibility of seeking out truth. And so to sort of take seriously this notion that, oh yeah, let's just pretend like nothing out there is even real or possible. What if we're all just in this solipsistic universe? Just seemed absurd and a waste of time. And so it left a really kind of bad taste for philosophy in my mouth. And it took me a while to get over it, but thankfully I was reintroduced in graduate school by some good friends. And started reading good philosophy, good history and philosophy of science, particularly some great Catholic authors. In fact, Stephen Barr's book was very influential in many ways. But given that, I still understand something of why someone like Stephen Hawking can say, in page 2 of his book, philosophy is dead, and then do 200 pages of philosophy. But, or someone like Neil deGrasse Tyson can talk about, can disparage philosophy as a waste of time, just sitting around asking questions about questions and not getting anywhere. Like, let's go do something useful and discover something. I understand where they're coming from, because I really do think that there are ways of doing philosophy that just aren't very helpful, that are in fact probably can be problematic, destructive. But the problem is, it's sort of been discussed in certain ways, in certain contexts. Whether you have thought about it or not, you have some sort of preconceived notion about the world before you ever enter into the lab or the classroom. And if you haven't thought deeply about that, you're probably not thinking about it well. And so there's a way in which philosophy can and should be a great foundation for all that we hope to do in this science, to make sure that we are on solid footing. I love physics and all the weirdness that it shows about the world, but I still had something of this gut instinct that any philosophy or any line of reasoning which somehow denied the existence of the real world or the existence of my mind or just my ability to choose to move my own thinking. It just was problematic, especially if you start using scientific arguments to undermine those things which are so essential to doing science at all. And so, now a gut instinct does not truth make. It's not a philosophy, and it's not necessarily right, but it has stuck with me. And that is what I found so refreshing about beginning again when I entered the Dominican, starting from scratch with philosophy and theology. And what I found so fascinating about the philosophy particularly of Aristotle and Aquinas. The thought of St. Thomas Aquinas, it would seem the portrayal he gave of the world seemed to mesh well with my gut instinct, give something of a language and a rigor to that instinct. And I found myself sort of stepping back and trying to look at the more complicated and weird things I studied in physics in the context of that philosophy. And so in particular, I loved sort of trying to take seriously, I loved how seriously Aristotle and Aquinas had taken the natural world around them. And that was, I found that in myself in my studies of physics. And so I found myself trying to sort of apply some of their physical principles, the things we've been talking about, to modern concepts. Now, of course, there is a slight difficulty here because, well, they were wrong. So in the context that, Aristotle's version of cosmology is just false. We're not going back to a restricted view of the world. We shouldn't. His notion of the four elements is just wrong. Fire, air, earth, water. It just doesn't work. This is the closest he gets to elementary particle physics. There's not even particles there. It's a weird continuum. So the details of the cosmos and the makeup of matter, those physical details that Aristotle and Aquinas relied upon are simply wrong. So there's no point in trying to directly go back and apply these things. That'd be silly. And I think everyone agrees here with that. But their physics in that ancient sense, in that sense of natural philosophy, I would argue, their study of nature is built on these more fundamental principles, rooted in more sort of basic fundamental questions that are still important in the way that we approach the world. So looking for basic principles, what it even means to say to move or to change. If you look at a physics textbook, there's no actual definition of motion. It's just assumed. In fact, if you look at Descartes simply just, motion. Everybody knows what motion is. Why do I even need to bother? Newton similarly. It's like, everybody knows what motion is. Let's just go. And yet there's trying to define motion and change without making it circular is difficult. And it's something that Aristotle and Aquinas took seriously. There's certain sort of fundamental principles that come out of these basic questions and considerations that I think are still helpful and relevant today. Now, I'm not saying that these are necessarily the best evangelical tools when you're talking to someone who's not familiar with them, but I think there is a role that they have to play in our understanding of the natural world. So I want to begin by trying to open up, for those who may not be familiar, particularly something that has come up, the notion of the four causes, in a context that hopefully is somewhat accessible. Now this is going to most likely simply just frustrate everyone, because all the Thomists in the room are just going to look at me askance and like, what the heck are you doing? And those of you who don't know what the four causes are probably going to be just confused from after, but we're going to go for it. So I'm going to tell you a story. This is the story of Junior and his dad. Junior's about 8 years old, and Dad is the source of all wisdom and knowledge in his life. So Junior comes up to Dad and asks Dad, why is the sky blue? Now Dad thinks, all right, I'm just going to nip this and just get done with this. Simply, because the sun's out. So why is the sky blue? Because the sun is shining. That's why the sky is blue. And in a certain sense, although even a child would know that the sky is only blue during the day, that statement is an expression of something important. It is a fact. The sky is only actually blue when the sun's out. The sun's down, it's black. You can't. It doesn't have the same color. And this is an answer to the question why. It's an answer. It's a because answer. It's an answer to a question about why is it that some natural phenomenon is happening that is correlative, is related to the notion of efficient causality or active cause. That there is something, the sun, acting in some way on the sky that makes it to be blue, be the color that it is. Now, unfortunately, Junior, being an 8-year-old, is not going to let that off so easily. He persists in asking, why is the sky blue during the day? So Dad replies, because the sky absorbs all sorts of light from the sun, and some of it gets showered down upon us. And this second reply touches on what is something something that we know about, classically talked about as finite causality, teleology. It talks about some natural tendency in air. Air left on its own is not blue. It is, in fact, it returns to this state of rest. That there is something about the air that is excited by the sun, and then it reacts by pushing off that excitation, the light, and that is an important part of the process of why it is that, it's not just the light coming from the sun that we see, but light from all sorts of different directions. So there's a way in which there is something of this excitation and return to rest, this tendency of natural things to seek out a certain rest state, a certain stable state in what they're trying to do, that we see in all sorts of nature. So, undeterred, Junior presses on with a simple, well, why? Why is it that the light? Why is it that the air reflects light in that way? Dad, seeing that things are getting serious, well, okay. So the sky is this big layer of air with lots of little parts, little particles of air, and any particular piece of sunlight might hit any particular piece of air and send it off in some random direction, some of it coming towards us. That there is this way in which it's something about the very structure of the sky, that it is made up of this layer, this complex layer of pieces and parts that make it so that the entire sky lights up. There's something about the form, we kind of broadly sort of that the structure of the sky that tells us what is going on and why it is that the sky is blue. Now, rather enjoying the worried look on Dad's face, Junior again replies with further reply. Well, okay, yeah, but why is the sky blue? Not willing to give up, Dad presses on, well, all right. So the molecules that make up the various gases in the air that's in this layer, the molecules that are made up are composed of things that are much, much smaller than the wavelength of visible light. And this shorter wavelength light, the blue light that is natural, that has a shorter wavelength, is just more easily refracted off of these molecules that are smaller. And that's why it is blue. So here we have an argument, broadly speaking, from matter, from what it is that is the stuff that makes up the air, the things that go into the constituents of air, the pieces and parts of air. And all the organization and activity of something is ultimately determined by its formal cause. It's not simply just pieces of, just the pieces and parts arranged in any such way, but in a particular way that brings it about. There are limits on the potential order and structure of how you can arrange any individual type of matter, any individual type of thing. For instance, the density and temperature of the air can be changed to create various weather patterns, to make the sky look very, very different. But there's no natural process that's going to force a bunch of air molecules to take on the form of hypotenuse. It's just, however delightful that would be to Junior, it's just not a physical possibility. There's something about the matter that limits the form, something about the form that gives the overall structure to the matter. So this is a kind of broad heuristic way of thinking about these four causes that are so fundamental to Aristotle. That it's they're answers to questions about why something happens. Why does something change? Why does some natural process happen? And that we can see how reasonable, perfectly scientific explanations of things can fit into these categories. That's not to say that we necessarily use them beforehand when determining the scientific explanations, but it's not necessarily so foreign that some of these natural processes could be, the answers to questions why this happens, can be structured in this notion of four causes. Now, of course, this is a very arbitrary and somewhat constructed example, and so it's hardly a proof of concept. And so I want to dive a little bit deeper into both the question of form and matter, and then later on to the question of sort of efficient cause and final causes. And to aid myself, I'm going to fall back into what I always do, which is when things get complicated, go to the simpler problem, namely elementary particle physics, obviously. So when you get to a less complicated situation, it's a way in which it makes more focused what exactly is at stake. It doesn't answer everything, but it's helpful in answering these sorts of questions. So So, as was mentioned briefly, an important aspect of related to the question of form and matter is in answering a question of how things change. And we've heard the discussion. There's, broadly speaking, in sort of an Aristotelian Thomistic context, two broad notions of how things change. There are changes where the thing that there is, in any sort of change, Aristotle will argue, there has to be something that continues from the beginning to the end. Otherwise, you don't actually have change. You just like something stopped being and something else started being. For him, that's not actually change, and that's not actually how we're going to talk about the natural world. That in any sort of change, there has to be something that carries through in this process. And so there are certain types of change where there's an obviously concrete thing that persists through that change. So if I go get a haircut, or I go outside and get sunburned, that does not change who I am as Father Thomas Davenport. Even though I willfully went to get that haircut, I have not become a different person in the process. And this is obvious to everyone. There's a way in which that is, broadly speaking, the notion of an accidental change. Not because I accidentally got my haircut, although I might have accidentally gotten a sunburn, but because the notion of a property that is not a concrete thing itself, but adheres in some sort of concrete thing, was talked about as an accident. There are these accidental changes where specific concrete things stay, but things about them, their color, their shape, their arrangement change, but the thing themselves is the same. Those are accidental changes. There are more fundamental kinds of change that we talk about as substantial change, where the very thing itself the very concrete thing itself does not persist through the change. A classical example of this would be death. That the human person before, the human person after death is not the same thing. Something radical has changed here. Or that there's a before and an after, and that there is something that persists, yes, but there is something that is radically different. Aristotle would argue that the thing that does persist in any sort of substantial change, is what he calls prime matter. Now, prime matter can be an odd and complicated topic. And so, again, I'm going to just jump back to the easiest solution and go to theoretical property physics. So, for Aristotle, the simplest sorts of substances, as I showed before, and there's the simplest substantial changes involve the four elements. So this is a little bit of that intellectual archaeology that we talked about before. But because I'm not trying to defend this, I just want to talk about what Aristotle actually said about the four elements, just briefly. So these elements are fire, air, earth, and water. And each of them were correlated with a pair of fundamental qualities. So air was fundamentally hot and wet. Water was fundamentally wet and cold. Earth, cold and dry. Now, these are not exactly the same as, hot, oh, I burned my hand on the stove. They're actually slightly, if you dig into how he talks about them, a bit more abstract. Hot is something of an active principle by which like things come together and different things separate apart. Cold is an active principle that tends to congeal different kinds of things together. Dry is sort of this passive principle why something sort of maintains a shape proper to it. Wet is a passive principle by which it just tends to take the shape of whatever container it has. Those are kind of odd notions, but the important thing to recognize is that he's talking about there's these pairs of active and passive principles that are what it is to be water, or air, or earth, or fire. The very form of air simply is being wet and hot. The very form of earth is to be cold and dry, to have these qualities. Now he believed that these were not, that these four elements were not impervious. They could change into one another, and it was easier to change when you shared something in common. So fire is hot and dry, air is hot and wet, and so it's fairly easy for fire to turn into air. Now, you could, in fact, turn completely from fire into water. That was a possibility he was open to, in which nothing, seemingly, of the qualities is maintained between them, but it was a lot harder. But the point being that the thing that underlies particularly the transitions from, say, fire to water or air to earth, there's nothing here to pin the commonality across these changes. There's no formal aspect of what it is to be air that is common to what it is to be earth, except being material, except being changeable. And so this is where that notion of prime matter kind of comes out most strongly. That prime matter was this, it was understood to be this substrate that was the continuous thing between the transitions between any substances, particularly air and earth, between fire and water. Prime matter in certainly could take on any form, potentially, but it was constrained by how it was active. So prime matter was not, now importantly though, prime matter was not a thing. Prime matter was not thought to be a substance of itself. It's not like you can go buy some prime matter, add some stuff to it to make air and water. It was the stuff that underlies everything, anything, any particular concrete thing had this underlying aspect to it, this underlying aspect of prime matter. So, so that's the picture that Aristotle gives, and it's wrong, right? It's just not true. Okay, great. Fast forward a few millennia. Beginning of the scientific revolution, and think about how people think about matter. And honestly, not much changed. Leading up before the scientific revolution, it was broadly speaking the four-element theory that prevailed. And this was in fact part of the frustration of many of the early modern philosophers and scientists. That it seemed like Aristotle's tools couldn't get you anywhere. You had this picture, the same picture for so long. I mean, Dr. Carroll talked a little bit about why that might have been different sociologists. Perhaps it was just a sociological thing, but for those early philosophers and early modern philosophers and scientists, they thought it was just a flawed system altogether. Let's get rid of the whole thing and start over. That's kind of what Descartes was actually going after. So Descartes, a brilliant mathematician who has solved geometry problems nobody has ever solved before. So he had this great idea. You know what? If I could make everything a geometry problem, I could solve anything. So he had this idea that if he could imagine the physical world to simply be a big geometry problem, he could solve any physical problem. So he had this idea that the very notion of what it means to be material was simply to be a volume, to be sort of some extended shape, perhaps very, very complicated, but that's just what it means to be matter. Matter was, in a certain sense, fundamentally inert. It was just this stuff, space that was filled, and one piece is pushing on another piece, and with that, he thought, I could turn this into a geometry problem and solve everything. And he tried really, really hard, and it's actually really fascinating. He comes up with this amazing vortex theory to explain planetary motion, to explain the stars, and it's this amazingly creative and beautiful story, this amazing creative picture, and it's just utterly wrong. It just doesn't work. He doesn't have enough degrees of freedom in his notion of what the fundamental stuff is. Simply saying that to be physical simply is to be extended, to be a volume, isn't enough. So we go first. So Newton recognized this, and he was open to the possibility of active and passive principles in the material order. Yes, things could push and bounce off one another, but there's more than just pushing and bouncing off one another. He was open to the notion of something, some sort of attractive force, obviously the notion of gravity. And something about, so something of an active principle by which one thing acts on another, and even something of a passive principle. The way he talks about, particularly the way he talks about mass and inertia, sort of leans towards being something of this a passive principle in things. So he's bringing back in some of these pictures of activity and passivity in the natural world. But he still, in fact, thought that all of matter was basically the same stuff. That all material things at root were made up of pieces of like little atoms, basically, that were all pretty much the same. All the same density. It's just how you rearrange them. They attract to one another, they bounce off one another, but it's just how you rearrange those pieces and parts that make up like all the physical interactions that we see. Now, it's important to recognize here that if we have a picture like Descartes or Newton about the world, arguably you could try to make an Aristotelian picture fit on that. But at fundamental, if everything is at root this unchangeable, indestructible thing, this concrete thing, an arrangement of these little concrete things, and all change is just a rearrangement of specific concrete things, then in an Aristotelian picture, all change is accidental. The very distinction between substantial and accidental changes goes away, because all you're doing is rearranging things. Rearranging things that are, arguably you could talk about them as substances, but so you may have substances, but you have no substantial change. All change simply becomes accidental. Now, Newton, again, had this notion that there was this complete uniformity in material order. And as chemistry develops, that kind of gets broadened. So Dalton kind of comes up with the idea, okay, well, maybe the atoms are all exactly the same, but they have, a distinction of maybe some are more dense than others or different weights than others, but still kind of hard, indestructible things. And as we develop into electromagnetism, as we develop into discovery of the electron, discovery of the atom, we recognize, okay, maybe these things we thought were so hard and indestructible aren't so hard and indestructible after all. Maybe it's the stuff that they're made of that's hard and indestructible. So maybe it's the electron or the protons that are the hard, indestructible thing that is the root of what's going on. So there's sort of trying to push down the layer of where we find that thing that we can rest, that substantial thing that we can rest our notion of what underlies all the physical bodies on. But the thing is, then quantum mechanics comes in and throws the whole thing for a loop. Jumping forward a bit, we get to a picture of the standard model of particle physics. So in some ways, this, it's a big square with little squares that label things. So in some ways, it seems very similar to what we talked about in the periodic table. You have all these, the basic particles of the standard model. But it's important to recognize two interesting facts about this. What do we know about these particles? We don't know anything about their shape or their size. What we know is something about how they act and interact. Something about their active and passive principles. There's something about sort of mass and spin that arguably can be seen as a passive principle, like how something reacts to being put in a situation. How mass is how something reacts to being pushed on or pulled on, or reacts to different different potentials. Spin as talking about how it is that groups of these particles tend to lump together, some sort of passive principle in a certain sense like that. Or active principles, like charge, like the color, like the different quantum numbers that physicists throw out there about how these things act and interact. So again, like we began to see with Newton as it gets developed, there's activity and passivity in these things. But even more so, these things aren't indestructible. Electrons aren't hard little bodies that never change. We have an instruction manual for how all of these things change into one another, the Lagrangian for the standard model. That there are ways in which one type of particle can turn into often a pair of two other particles. And certain of those transitions are easier or harder, depending upon the particular active and passive principles that thing has. There's a way in which there is this changeability, this changeability even at that most fundamental level of what's going on. Now, the question is, okay, well, is there anything that fundamentally is underlying all of that change? And physicists would probably say yes. There is the energy. There is this conservation of energy. Now, energy is a weird thing. Physicists use it a lot, and we have a good concept, we have a good idea about it, but it's hard to explain what exactly energy is, because you don't ever just find energy. You don't just go to the store and buy energy. Energy always exists in some particular instantiation, some particular form. So you have the energy that exists as a Z boson, as a tau, as a tau lepton. Energy that exists in kinetic energy, in the motion of something. Energy that exists in potentials, the mutual interaction of things. That energy is, the power of energy is that it is this underlying thing that helps to tie together all the different changes that go on in the physical order. So energy is not exactly the same as prime matter. I'm not trying to make that claim. And yet, there is something about this picture of fundamental constituents of the physical order that are primarily characterized by active and passive principles that have some other thing that we can never actually get to as a thing, as a separate entity that underlies all of those changes. That's not the four-element theory, but it's also not so different from some of the principles that underlie the way, the structure of the four-element theory. In fact, it's closer to that than arguably Descartes' system for sure, and even the Newtonian ideas and the early ideas about atomism. So there's a way in which, taking a page from Dr. Barr's great book, Modern Physics, Ancient Faith, I'm making the argument that there's something about modern physics that is actually more conducive to some of the classical Aristotelian ideas than the classical physics that came before it. Does that mean that everything about Aristotle was right? No, of course not. But there's something useful in seeing that connection. How are we doing on time?
20 minutes.
All right, great.
15.
All right. I might start making stuff up at the end. So there's one other area I want to focus on. And so I talked sort of a little bit about, broadly speaking, material and formal aspects of reality. I want to talk a little bit about efficient and final causality as well, sort of these other notions. So for Aristotle, so first off, there's just something of a misconception about teleology. If you've heard this phrase, often it's, in some contexts it's pejorative, in some contexts it's great. There are different layers in which we think about teleology. The most obvious layer in which we think about teleology is we choose to do things. So I'm up here waving my little finger because I'm obsessed with waving my little finger when I'm making a point. I chose to do this, I'm doing it, there's intentionality, I have a desire for some absurd reason to wave my little finger, and my little finger is waving. There is teleology, there is an end that I'm aiming after, hopefully convincing you of something, and so I do something to get to that end. We see a lesser sense of that, a similar but lesser sense of that, I argue, in animals, in the way that they can chase after things they want or run away from things they don't want. You can see something of this ordering towards some end in the biological order, just the very nature of growth, that a seed grows up to become an oak tree, that there is some perfection, some good it is moving towards. And so sometimes when you try to talk about teleology on just in certain inner level, it seems odd, because you don't see that intentionality. You don't see things choosing things, because it turns out this doesn't really choose things, it just follows them. But inner things don't actually choose to move. But if you look at the way that Aristotle and Aquinas talk about teleology, at the basic level, at the lowest level, there is simply a tendency towards an end, a tendency towards usually some rest, some stability, some aspect of stillness or something. That is the basic notion of teleology. It's not that the rock falls because it wants to fall, but it's aiming towards, it tends towards a place where it will be stable and not moving. And that place tends to usually be down. So in the Aristotelian cosmology, again, he took this notion of this motion towards end and just fit it into this perfectly spherical cosmology, saying that it's a little hard to see here, but that once you get past all of the completely impenetrable heavenly spheres, which are clearly out there, you get these layers. That fire is the stuff that tends to go up, and so the fire is going to tend to be at the top. That the air is going to be below that because it goes up, but it doesn't go up as much as fire. Water is going to be below that, and the earth is going to be at the bottom. And so one of the primary principles of dynamics for Aristotle was this tendency towards an end. There's efficient causality in there as well, in the way that things are given these tendencies, but he primarily thinks about dynamics in a teleological sense. Now, you don't end up with these perfect spheres. We've got a perfectly spherical layer of earth and spherical layer of water. You get weather and complicated things in the sky because all of this stuff is getting mixed up by these random spheres. So there are other principles besides just the teleological principle. I mean, there's the violent, efficient causality of the heavenly spheres moving things around. But there's something fundamentally teleological about how he thinks about dynamics. Newton completely rejects this. And in some sense, rightly so. The genius of Newton is to talk about motion in this context of, rather than focusing on teleology, to focus on the context of, to focus on the efficient, to focus on forces and how forces affect how things move. So we have this impressive aspect of the Newton's laws that the F equals ma, that we can see, we have some massive object. When something pushes on it, some efficient causality is acting on it, this is how it's going to react. And we can describe motion. He wanted to describe motion purely in terms of efficient causality. And in a certain sense, you could take this to the extreme. And the best expression of this, I think, is what's classically Laplace's demon, although he doesn't talk about it as demon. He said, we may regard the present state of the universe as the effect of its past and the cause of its future. An intellect which at a certain moment would know all forces that set nature in motion and all positions of all items on which nature is composed. If this intellect were also vast enough to submit this data to analysis, it would embrace in a single formula the movements of the greatest bodies of the universe and that of the tiniest atom. For such an intellect, nothing would be uncertain in the future, just like the past would be present before our eyes. So Laplace takes this notion of, okay, if we just knew all the forces and all the masses, we could solve everything. We could actually build this deterministic picture of how things work. And so there's a way in which Newton's structure, the way that Newton came to describe dynamical laws, leaned towards this deterministic view of how the natural world works. But the thing is, this picture comes in before other developments that come in physics, particularly developments related to potential energy and the very notion of energy as a whole. Because there are other ways besides Newton's laws that we can think about where exactly things are going to end up, or how things get to where they are. So if I have this cup and kind of hold it at a tilt, if I dropped, I'm not going to do this, but if I dropped a little coin in here, I know where the coin's going to end up. It's going to end up at the lowest point. There's an aspect of the change of potential energy and kinetic energy of seeking out the lowest energy state. That there's this tendency towards this lowest state of rest when you talk about when you talk about potential energies and how things act on potential energies. And in fact, actually, you can do more than that with what's called the least action principle with Hamiltonian dynamics. You can actually not simply figure out, get a good rough estimate of where you think things are going to end up based off of minimizing energy. You can actually figure out how they're going to get there. You can actually derive all the same dynamics that you get from Newton's laws using this other formalism that focuses on this minimization of what's called the action, this minimization of this combination of kinetic and potential energy. That it just is the case in classical physics that if you just calculate out what the total the action across any particular path, you find that path where if you change it a little bit, it's going to be stationary, it's going to be at some minimum point. That's the path the thing is going to take. It's the same path you would get if you restructured the whole thing in terms of Newton's laws. Now, this is just as deterministic in a certain sense as Newton's laws. There's one path that a thing takes to get from initial point to final point. But what's fascinating and important is that this is the pathway that led to and opened up to quantum mechanics, not the pathway that Newton. You don't start from F equals ma directly, and historically you don't start from Newton's laws to get to quantum mechanics. It is in fact taking something of this line and saying, okay, well very roughly, sorry. If you say, okay, instead of just finding the one minimum path, if we just use and say, okay, each of those paths is a probability. The probability of the thing taking this particular path. This becomes the Feynman path integral formalism for how particles travel. That we, in modern physics, in quantum field theory, and the way that we do particle physics, uses this formalism rather than the F equals ma, the notion of forces and masses and accelerations directly. That there is something about this formalism which is more about a tendency towards something, not exactly rest, but tendency towards stability, tendency towards a certain state that is more conducive to actual advances in physics than the completely deterministic view that is, or that comes directly from Newton's laws. Not, I should say completely deterministic, but the generally deterministic view that comes from Newton's laws. So that there's a way in which being open to, this is not teleological exactly, but being open to this notion of tendency towards things as a fundamental principle of how nature works, in fact, helped arguably in certain advances in physics. I want to, so I'm going to try and tie this up. So the 2 points I want to finish up with. One is the big difficulty, the great power of physics is that the world actually obeys mathematical laws. That is utterly fascinating. Like, why should that be? That is amazing. That the physical world actually obeys ordered mathematical laws is fascinating. But the weird thing is sometimes it obeys really different looking mathematical structures. That the same physics can be expressed in different mathematical structures, and on the surface of it, you can't necessarily tell which is better. And sometimes a single mathematical formalism that explains one aspect of a problem really well leaves you completely dumbfounded about another aspect. This is, in a certain sense, the difficulty that comes in with quantum mechanics. That we gain so much in the indeterminacy that we see in quantum mechanics by having to give up certain aspects of the knowledge we would kind of like to have. That there are great gains, but this leads into the problem of how do you interpret exactly what is going on in quantum mechanics. And so you go to the Wikipedia page on interpretation of quantum mechanics, and you find 10 million different instances of this. And they're all, roughly speaking, mathematically equivalent. Now there's certain ones you could experimentally differentiate, things like that. But that physics, using the power of mathematics, leads us very, very far. But it only leads us so far. That there's something about sort of fundamental philosophical questions that can't simply be answered purely on the mathematical scale. And so my rough argument is that we should be open to various philosophical tools that might help us to understand these things better. Will they necessarily help us solve physics problems better? Maybe not, but maybe they will. Maybe they'll point more towards one particular formalism than another that might lead us to that next step. The last thing I say, just sort of slightly in response to Steve Barr, and I in fact agree in many ways with a lot of what Steve has to say. That I would not walk up to my old colleagues and friends at Stanford and start talking about, all right, let me talk to you about formal causality. You know that. All right, let me sit down and explain what formal causality. That's not the best way to go about it. And sometimes it's, in fact, it can be a hindrance. The language in particular can be a hindrance. But I think the concepts are important for a number of reasons. One, simply the very possibility that they might be the way to that next, that clarify something about that next step. Maybe they aren't, but they might be. And secondly, that a lot of these philosophical concepts, these natural philosophical concepts that are talking about the natural order, have huge theological implications and actually underlie the way that the church has thought deeply and coherently about hugely important things like the Trinity, like who Jesus Christ is in Christology, about the Eucharist, about sacraments in general. That so much of a lot of our language about how we think about theological topics is really closely connected to this tradition of speaking about the natural order. And it would be a shame to simply to lose that. I'm not saying that Steve is claiming we need to do that. He's faithful to the church, and so I'm not trying to make anything like that. But I think that there is great value in the way that the natural philosophical principles of Aquinas lead into his theology. That is important to at least try to hold on to as best we can. And I would argue that it can be done. And since I'm sure you aren't convinced, I'm going to give you the weakest form of argument, which is an argument from authority. and saying there's this really awesome book, several people of whom have wrote articles for it. It's Neo-Aristotelian Perspectives on Contemporary Physics. The first half is physics, the second half is biology. I've only read the first half because I'm lazy, but it's awesome. I'm not saying they're all right, but it's taking seriously this call. Okay, what can we salvage of the Aristotelian structure in serious dialogue with what's going on in modern physics? So this may very well be a fool's errand, but if it is, I hope you will accept that I am not a fool for Aristotle, but a fool for God.